What is up? Man, I'm glad everybody was able to get a seat. For those standing in the back, I apologize. We're going to go ahead and get started. So I'm Oscar Boykin. I'm from Twitter. I'm here talking about Summingbird, which is a streaming MapReduce system that we have, which has a lot of nice properties, which we're super excited about. So first I want to talk about what Summingbird is. Then we're going to talk about why you want it, and then I'm going to talk about how we use it. So the first thing that Summingbird is a model for streaming MapReduce, multi-stage MapReduce, large flows in general. So the second thing, that's disappointing, that Summingbird is an implementation of this model of streaming MapReduce on a number of platforms. So right now we have Storm, we have Hadoop, by way of cascading and scalding. We've got a preliminary Spark implementation. This summer, we have a Google Summer of Code student working on a native Tez implementation. We've had some Sketch implementations of Akka in the past. It's relatively easy to port. I would love to see a Samza implementation. Okay. So the key thing to take away from this is that we have this model for what these flows look like that allow you to run both in real time and as you can see, in batch. But we also, it's incredibly portable. So we've already ported it to many, many different applications. We'll see in a moment why we're so excited about that. So the next thing that Summingbird is, it's a systematic implementation of the Lambda architecture. I'm going to go in detail what that is, but the Lambda architecture is an approach for designing distributed systems such that you can run a combined real-time system and a batch system in a way that gets you very up-to-the-moment results and also gives them to you in a fault-tolerant way. Okay, so that blue, ideally, if the slides were going to be shown as they were on my laptop, would have been around the Lambda architecture. But that's what you get when you just hand your slides over. Okay, so what do I mean by streaming MapReduce? So here's a graph that we can represent directly in Summingbird. So I've tried to make the shapes mean something and the colors kind of mean something. So the triangles at the top, those are sources. Those are places where events enter the system. The hexagons are mapping operations. That diamond there is a lookup from an external service that's going to hydrate some data. We can merge this data together, and then finally that kind of rounded square is doing some kind of aggregation. So we can do big topologies like this. We can keep going. We can keep as many of these that you want to compose, you can put in. So merges, lookups, which are very similar to joins, aggregations, and you can just keep doing this. And there's a few key concepts that you see. There's sources and services. This is where data enter the system. So a source is a stream of events that come to you one at a time in a sequence in time. And a service is something that you can go and look up, generally by key. So give me the user whose ID is X, or give me the recent geodata for the country whose country code is Y, so forth. I didn't display it here, but the dual of the source is the sink. So you can also write out a stream of data. And the dual of the service, the way to materialize a new service, is the store. And that's what's going on in the aggregation where we sum by key. So the service and stores are keyed, and the sources and sinks are not necessarily. These are just events, timed events. So what do we mean by streaming here, and how is this different than what you might have seen in, say, something like Scalding or Spark or any other models that you might have seen? What I mean by streaming in this case is that we can pull one event at a time out of the source and push it all the way through this topology and sensibly update the state of that topology. So it makes sense one at a time. It doesn't necessarily mean that we always run this in a real-time mode. We can run it on Hadoop where we take a batch of inputs and jam them all through, and we might get an efficiency gain by doing that. But in principle, the logic that you're specifying made sense one item at a time. So that means conceptually, this is they're all incremental updates. Now, I don't know how many people we have working on systems in the audience versus how many people we have using things versus judging by the keynote, a lot of people were just buying things. But the systems people will always look at this and go, I don't know, like I probably want to do some other thing and like whatever. And what we found is like 95% of the analytics loads at Twitter can be fit into this model. Now, certainly you can describe systems that won't fit into this model, but we found that the vast majority will. And for those, we can highly optimize them and make them incredibly robust. So we're very satisfied with that. Actually, I'm really satisfied with it, and just by force of personality, I've forced these guys in the front row to be satisfied. Okay, so what does it look like if you're the first group, I think it was, the people who are using it, and not maybe the systems guys, I don't remember or people, I don't remember the order in which I said. So here's a very simple Summingbird job. So this is written in Scala. You can also write Summingbird jobs in Java. With Java 8, it won't look very different than this, but here's the Scala picture. So this is the word count job. And notice it's totally, so P represents what platform you're on. When we run this, the value of P might be Storm, or it might be Scalding, or it might be Spark. We've implemented all those and run those on our cluster. But P represents what platform you're on, and this logic doesn't care about that. Next, you have the producer. This is just something that's going to emit events. So the source is our producer here. It's a producer for platform P. That guarantees I don't like mismatch my Spark event stream with a Hadoop event. They obviously don't make sense together. And then I've got a store that I'm going to write it out to. And this store is, for that platform, a store means different things. So that syntax there just means on platform P, whatever the store is, you're going to give me one. And this store stores with keys, strings, and values longs. Because, as we all know, Hadoop is strictly a system for counting words. Here we go. I'm going to take my source, and as long as the text in that source, this is a status. So at Twitter, obviously, we're all like super pumped about tweets, call them status. As long as there's some text associated with that tweet, I want to tokenize it and then count the words. So there it is. I'm going to filter out all the status updates that don't have text, just to demonstrate a filter, really. And then I'm going to expand the tweet, which is just the status message, the text of it, out. So if you're not familiar with Scala, you might not know the flat map thing. It's just a map operation followed by a flat. And if you're much more of a Java Hadoop developer, it's exactly what Hadoop can do on the mapper phase. I give you an item out of an iterator, and you can emit 0 or more items. And that's exactly what flat map means. It's just what the Scala community calls that operation. So inside that, I'm actually not just going to emit each word. And tokenize is just some method I wrote somewhere else. It can be a Java method. It can be written in Scala. It can be whatever. But I'm going to take that tokenize, which is going to return, say, an array or a list of words that were in that tweet, and I'm going to map that onto the pair word, comma, 1. 1 because I've seen it one more time, okay? And 1L is it's a long, okay? And then I just sum all of those by key. So that just means group by key and then sum. Sum in this case is going to mean take the longs and add them up numerically, and we're good. So that's what the jobs look like. The weird thing is, probably not the surprising thing, is the logic. This allows us to express logic so concisely that you really see the logic kind of fade in the background. And I think one of the big challenges we have in this space is how to deal with all the configurations. They start to become front and center. How do you tune how many mappers, how many reducers, if you're running online, how much, how big are your buffers, et cetera, and so forth. So, but the job logic can be relatively self-contained and very portable. Okay, we have a lot of other operations that you can do other than map and sum by key, and here are some of them. They're very, very common to this kind of what people have been calling the distributed collections model. I don't want to really go into them in detail and talk about that, but this is on GitHub, Summingbird, Twitter, and you can see all of them there. But most of the common things that you're familiar with are going to be there. A couple of the limitations that we've imposed to keep the streaming concept in place are that for joins, we really have a very simple join, and we call this left join. But it's really a little bit of an abuse of a term. What it means is that when an item comes down with a certain key, we're going to look up in a service and see if that key has a value associated with it. If there is a value, we're going to associate, if you're familiar with optional types, the non-empty value. Yes, it's there. Or if it's not, if it's absent, we're going to associate the empty type. So it's a very weak concept of join. It's like joining with the most recent value. But that's by far the most common thing. A full cross-product join that you might be familiar with doesn't really scale very well or turn out to be that useful in streaming contexts. So we haven't found this to be a big limitation. Okay. So why would I want this? So when we talk about this, a lot of people say, well, should I use Kafka or should I use HDFS? You know, like these sometimes like nonsensical questions and comparisons. But where does Summingbird fit into this picture? And Summingbird is, we have all these jobs and we see technology changing and we want to be able to code against one API that can like move with us. That's one motivation for this. So if we adopt this model, the Summingbird model that has this semantics of one at a time streaming, then this model makes sense both in real time and offline. Even if many teams just use it offline, they just use it on Hadoop, they know that if they needed to, they could take that same code and run it on the Storm cluster. Okay, so that's one motivation for why you want this kind of abstraction layer. Okay, so that's been very successful. So a little bit of a restatement of what I was just saying there. But we're able to go from like the Storm. We anticipate it would be really easy to port this to Spark streaming. We can move code from Hadoop to Spark, again, without changing any of the job logic or knowing that we need to retest any of that. And we are really excited to get our TES back in going this summer, as I mentioned. So two, we can implement optimizers at this logical layer. Okay, so optimizers are not a lot of fun to write. Well, I mean, actually, a lot of people love to write them, but they're actually hard and they take a lot of time. So it's nice that we can write this optimization layer once and apply it across many different platforms. And a lot of the conceptual optimizations work the same. For instance, a very common optimization is for commutative operations, pushing reductions onto the map side is a huge, huge help. So in Hadoop, that means like using something like a combiner or an in-memory combiner and pushing that up to the mappers. But that actually also works well with Spark, well, surely it works with Spark as well, but with Storm as well. And with Storm, it's incredibly important because we're trying to process in real time and keep up with these streams. And so if we can reduce the number of key value pairs that we emit in a mapper, it's a huge, huge win. We've noticed a couple of nice data cubing optimizations. If you're going to do data cubing, where you have like a user comes in, they're in a particular geo, they're in a particular age group, and they've looked at a particular page, and you want to cube that out, like and go from this page to all page rollups, and this geo to all geos, or even regional hierarchical geos, you might expand this one event out from 8 to maybe, even, some of these rollups go out 1,000 ways, like 1024. You can actually do that map side aggregation before you do the expansion. That map side that data cubing is only expanding out in the key space. It's not changing the values at all. So you want to, the optimization you want to do there is to move your map side combining in front of that. Again, this is a little bit of a tricky thing. You don't want to have to necessarily do on all your platforms. We get it at one place. Okay, so last reason that we were excited about this model is that if we restrict our reduce operators to a rather broad but like lawful and algebraic class, we can automatically build a Lambda architecture system. This is that Lambda architecture system that I mentioned, gives you like real-time data, but also fault-tolerant, nice fallback properties. I'll discuss it in details right now. So what is this Lambda architecture? I resisted this name for the longest time because I hate marketing, but oh well, that's what Nathan calls it. Great. Lambda architecture is a name given by Nathan Mars, and it looks like this. This is taken from the lambdaarchitecture.net. And you have your data come in. I think it's an idea that many people have rediscovered. In fact, Marius at work pointed me to someone who, like back in the 60s, apparently, there was this description of this bank transaction system where they would try to keep all their ledgers up to date as the cashiers were working. And then every night when the cashiers would go home, they would do their batch like update that was super careful and commit the data and throw away the real-time stuff that the tellers had done in the 60s. So this was, it's an old idea that you write your data twice. Once you write it onto HDFS, let's imagine item 1 on new data, this picture is a queue of events that come in from some system. Let's specifically imagine it's Kafka. So we've got one process that reads and writes into 2. So what it's going to do is it's going to read out and then write onto HDFS. That's great. And this is the system of record. The second one is going to be the speed layer. That's marked 4. It's at the bottom. It's going to read these Kafka events as quickly as possible and then apply some whatever transformations and aggregations you're going to want to do. Finally, the real-time layer is going to write into its real-time view. That's the next thing over in box 4. And at some point in the future, the batch layer is going to write some kind of batch commit of its latest updates of this data. Now, lastly, at query time, you read both the batch view and the real-time view, and you do some kind of merging. So this all looks pretty good. It's like, oh, that's awesome. But if you look at like, well, how the hell do I do that? I mean, like that, you know, you haven't told me anything. You just kind of vaguely sketched this. Like, how do I integrate at the query time? Like, what does that look like? What kind of operations can I fit into this model? It's not so clear. So that's the problem that, you know, if everyone goes and builds a new one-off Lambda architecture, it's very difficult for us to like scale those out and to port them. And like they have these, like generally you write the logic twice, once on Hadoop, once on Storm. It's a pain. So what we noticed was, and I'm going to keep the functional programming to an absolute minimum. All I'm going to say is monoid. What we noticed is that monoids, or associative operators, have a property that you can leverage for building the Lambda architecture and make it so that you don't have to worry about anything else. If we limit our reductions to associative operators, which turn out to be like not a strong limitation, we can do many, many things with them, we can build the Lambda architecture for free. And that's pretty cool. That's super cool. So here's what the associative operator looks like. You go 1 plus 2 plus 3 equals 6. And everyone knows like how addition works, so much so that they don't even notice these things, but there's this property called associativity. So if I were to first add 2 and 3 together and get 5, you see that 1 plus 5 equals 6. But I could have also done it the other way. I could have done 1 plus 2 equals 3 and 3 plus 3 equals 6. So that property, just that it doesn't matter which way you do that, is called associativity. And many, many operations have this property. Many operations. And those that don't have that property often have an approximate version that have that property. So we wanted to exploit that. So if you're saying, well, what has that property? Well, here's just a small list of them. We have many of these implemented in a project called Algebird, which is now the second most ridiculous bird name at Twitter. I thought that would never be topped, but a new project I'm working on has even gone one more with distributed. I don't know how I'll top distributed for most ridiculous bird name, but if you have any ideas, please see me afterwards. So almost anything that you can do on like normal operations, like many, many things, if they take 2 of the same type and return that type, very often it's associative. So min, max, addition, multiplication, set union, set intersection, even harmonic sum, strangely, is associative. It looks so complicated. Well, it looks somewhat complicated. You'd be surprised. 2 that we really love because they're like, you know, fancy and make us again look like functional programming hipsters are hyperlog log and count-min sketch. And hyperlog log gives you approximate unique counts. If you want to know how many users came in 1 hour, and you want to aggregate those, the naive way is to build a set and then just do distinct on that set. If you count how many there were and then record that number, okay, there were 100, in the next hour you find 110. Now, do you have 210 total in 2 hours, or was it all the same 100 from the first hour and just 10 more? So hyperlog log has the property that you can retain a small amount of data, slightly larger, maybe a few tens of kilobytes, not just like 4 bytes. But tens of kilobytes, and summarize how many have been there such that you can combine them associatively in this way in the next hour. It's incredibly powerful, and we use it all the time. Count-min sketch does something similar for counters. You want to know how many times a particular event has occurred or how many times a user has come. But you don't want to build the whole table of all your, trillions of users. I'm not supposed to admit that Twitter now has over 1 trillion users, but apparently that's the case. That's a joke, people. There are not 1 trillion people on Earth. And for anyone watching that is not, I'm not even supposed to make those jokes. I'm sorry, I apologize. Vectors. If you've got a vector, you can point-wise do this operation, you've still got a monoid. So monoids are incredibly powerful, incredibly general, not really interested in someone raising their hand going, what about this? Is that a monoid? I'm just going to say yes, it is, even if it's not. Okay. So how does this monoid give you the Lambda architecture? So that's the question. So this is the Lambda architecture picture as before, except I've put the log source in the middle. And I've batched them up according to time. So batch 0 is some like time, like, we know some boundary happens and we've ended batch 0. And then batch 1 happens and then batch 2, et cetera. Okay? Now we fork the data out. One of them goes up to the RT, that's the real time. This might be Spark Streaming, it might be Storm, it might be whatever system that you have, whatever you like. And we do these aggregates. And in each batch, the real time starts summing from 0 again. So the key thing is that batch 0 to batch 1 is never contaminating one another in the real-time world. And though I think I left the arrows out, in the Hadoop world, that's our transactional mode. That's the one that's updating as it goes. So batch 0 is computed, and there should have been an arrow between batch 0 and batch 1, because Hadoop will look at batch 0 and the new data, and then from that compute the new batch 1. Okay? So the Hadoop, or any batch system that you have, is presumably reliable, fault-tolerant, transactional. Okay? But it may be behind. I find that it's very difficult to get a Hadoop stream available to serve in with less than an hour of latency. So it's a little bit challenging to have real-time data coming in and be able to serve that in less than an hour. Probably you can do it. I don't know what the minimum anyone's been doing out there. Maybe you can do 20 minutes. I don't know, but it's a little bit of a challenge to get through your job, depending on your clusters, et cetera. So how do we then do the query layer? Remember, that was the last part of the Lambda architecture. You query from both sides. So hypothetically, you could take this Hadoop data, push it into, say, HBase, and then read that as a serving layer, but it's not up to date. And so you read, say, the real time is writing into, let's, for instance, imagine Memcache. So we do these two reads. I read from Memcache, I read a little bit from HBase, and due to that associativity property, I know that I can do that last addition of these two values that I get, and it will be the exact same value as had I done all of them back to back. That's where we're getting that monoid. So cool. All right. So here's what the Summingbird picture looks like for the Lambda architecture. So we very often use Kafka, or a queuing system that we also use called Kestrel. We have some process that will take the Kestrel logs and then write it onto HDFS, and there's the batch layer. If you look up the GitHub project, you'll see the Summingbird scalding. We chose to actually implement the Hadoop layer on top of scalding, partly because we spend a lot of time working on scalding. We know it really well, and it does a lot of the stuff. But you could have done it directly on top of Hadoop, as we're going to do this summer with Summingbird Tez. And then you can push this over to a layer that we read with the read side of this project is called Storehouse. It's also on GitHub. You can use it outside of Summingbird, and many people do. We use a different store other than HBase, something you might have read about in Wired called Manhattan, but it's basically effectively, conceptually the same thing. Now down at the bottom, we run on top of Storm. So Storm doesn't have, as we heard, I don't know if you went to the talk this morning, that Storm doesn't have such a strict MapReduce model. It has these notion of spouts and bolts, and it doesn't have quite as clear semantics. It's more of a system for designing a distributed graph of how tuples are going to move through the space. But we actually push it back and make this MapReduce model just scheduled right on top of it. So we do a lot of optimizations that try to minimize the number of bolts that we render, et cetera. And we can get actually really good performance out of our Summingbird topologies on Storm because we have this optimization layer that Storm's really going to do what you tell it. It's not going to do any amount of minimization of the number of bolts that it builds, et cetera. So then we generally run the Storm to write into either Memcache or Redis, or in some case, again, our Manhattan store can also do read-write now. So some people use that, but it's very, very portable. You plug in the backend that you like. It's not very difficult to do. And then at read time, we have systems that will then, this is part of storehouse algebra, it knows about this algebraic property of the monoid, and it can merge them back together. Okay, so that's the Lambda architecture. So the cool thing is you didn't have to think too much about this at the logical layer. In fact, you didn't have to think about it at all. Once you follow the rules of Summingbird, Summingbird will not let you write something currently that you cannot automatically build into this Lambda architecture, which is pretty cool. Okay, so what have we done with it? What's Twitter's use case for this? So we built many things with it. We build a lot of ads dashboards, both internal and customer facing. We've got operations dashboards that help us understand the state of Twitter at given times. We have things that we publish for publishers who are not exactly advertisers, who want to know analytics about like how their links and tweets are doing, how we're driving content to them, etc. There's also just straight up stream transformation, where you don't really care that much about this whole monoid thing, and you're just going to do some filtering and some mapping and some joining with external sources and hydrating them and exporting them back to another Kafka queue. But we have so many developers that are very familiar with the functional style of just mapping and filtering and dealing with inline lambdas that this approach works really well. And again, it separates the business logic from the configuration logic. We don't do a lot of training of models with it yet, but we do build real-time features for those models. So once you've trained a machine learning model, keeping real-time counts so you can do better ad targeting and better content recommendations is something we do a lot. And lastly, a really nice application are top K applications. So you want to be running in real time and seeing like what tweets are being retweeted most at this moment, what URLs are most interesting right at this moment. And those top K applications are pretty cool. So for instance, one of them that was one of the first adopters of Summingbird internally was looking at embeds of tweets. So for a long time, I guess I need to do the update this slide to the Ellen tweet, the selfie tweet. But Obama's 4 more years tweet, this picture, and then 4 more years, you see there at the bottom, there's an opportunity to embed that tweet. So if you click that and click embed and put that on a web page, this whole tweet will appear on the page. And so these pages are then driving traffic to Twitter. But if you then just look at the tweet, we'd like to be able to drive traffic back to the sources of this. Where on the web are they talking about this tweet? So that's an interesting problem. How could we do this in real time? Okay. So this is the Summingbird topology. It's a very simple topology, really, that we built to deal with this. So we have well, these are not actually tweets, but these are records of tweets being embedded coming in. And they're coming in from our queue, an HDFS. It's being written to HDFS, and it's being materialized on a Kafka queue. And now we do this flat map operation. Here's where your mappers go, okay? And they're going to map each tweet onto a key value pair. The key is the tweet ID, and the value is this approximate counter. And I don't really want to go, I don't have time to go into the count min sketch algorithm right now. But if you are familiar with Python, there's this counter type. And just imagine that you've got a key and there's a value that's a number. And obviously you can add those together in a very clear way. Or if you're familiar with Hadoop, there are these things called Hadoop counters. And it's very, very similar to that. So the count min sketch takes a key as the domain. And then we've seen this domain point at this tweet one more time. And just to keep an all count, we don't have a tweet ID 0, so we do the normal CS hack of jamming things in with poor schemas and using 0 as a key to represent all tweets. If we're just interested in seeing what are the top domains embedding tweets. So once we've mapped them in that way, we then do a group by operation that groups by tweet ID. So now each of our reducers is going to see only the stream for a given tweet ID. And that tweet ID, the reduction operation is going to be, again, this monoid. It's going to add them together so if you can add counters together in exactly the same way that Hadoop does. The mappers ship their counters over to the job tracker, and you can merge those. So exactly logically, the same way that you would merge those counters is how this is being merged. Only internally, it's approximately this approximate data structure. It's really, really nice. This approximate data structure, the count min sketch, it doesn't keep all of it in memory, but one nice thing it'll do is it'll tell you the top values, the biggest values exactly. So which domains have really embedded a ton? Which are the heavy hitters? Which are the top K? So with that top K, these heavy hitters, we're able to render a nice UI. So if you like, by the way, you can add a time bucket to the key. In this key, this is a very simplified kind of cartoonish version of this job. Rather than just keeping the tweet ID, you could do the data cubing thing, where you have this tweet ID in this minute, and in this hour, and in this day, and in this year, and so forth. And that data cubing, we call that flat mapping to keys. We know how to deal with the optimization here at the Summingbird layer, but then we can deal time series as well. In fact, that's what we do. We do have the time series. So once we've done that, and we've got our time bucket keeping track of history, we can, there there was supposed to be the thing. Anyways, and the punchline is search Google for, that's so sad that I say that, search Google for 4 more years Obama tweet, and you'll find that tweet, and beneath it, you'll see the places that embed it, and that embed list is exactly generated by this process. Or if you look at the Ellen selfie tweet, and you can see under it, when you go to the tweets page, the permalink page that just shows the big tweet, underneath it, you'll see these recently updated links live of who's embedding that tweet, which is very, very cool. So I'm going to review what Summingbird is. I've left plenty of time for questions or, coffee. So we got this portability and optimization layer. So people are worried, should I be coding to Spark? Should I be coding to Tez? Should I be coding to Scalding? Should I be just doing all this in SQL? We've got this one layer that if we code this logic in, we can render them on most of these backends relatively easily. And that's been nice because we've been able to move some things. The second thing that we got out of this was, again, this Lambda architecture. So we have this huge fault tolerance. We've got these systems running on Storm. We've got them running on Hadoop. And when the Storm system goes down or we need to restart it, we've still got relatively recent data from Hadoop. It's relatively rare that the whole Hadoop system goes down because we've invested much more in that reliability story. So these systems have been very, very reliable. So the teams that have to own them really like dealing with these once they get them up. And lastly, because we've been able to really hammer on these optimizations on this restricted graph of what we allow, the streaming MapReduce with associative reduce operations, we've got a lot of nice optimizations in there, and we can deal with totally Twitter scale with relatively minor hiccups. Only the jobs that do the biggest expansions, the most giant data cubing, have we really had to lean on. And in no case have we not been able to put a job that we wanted to into this framework. And so there we go. So if you're looking for how to learn more about it or how to get involved with it, so you can follow Summingbird on Twitter. We have a Google group. We're on IRC. We're on GitHub. There's the GitHub page to the right, and we got this really cool logo with the Sigma, obviously, for the sum and the bird. All right. If you think this is cool, Twitter's hiring. So come work on Scalding and Summingbird and follow me or email me about that or Summingbird or how all of my jokes, full stop, fell flat this time. And how you heard he was a good speaker, but it just fell through. Anyways, thanks a lot. I'll entertain questions at this time. Yes. I heard the first part, and I will repeat his question if it's not 30 lines long, or there may be a mic over there, or over here. Yes. It's something to do with the Lambda architecture, though. That's the tease. Go ahead.
So in the Lambda architecture, you always read your raw data rather than reading in your pre-aggregated data. But kind of in the slide, you gave the impression that the input for batch 1 was the output of batch 0. So is that the case, or do you actually always go back and read in your raw data?
Okay, so the question was about, and this thing is just not going backwards. There's no more. It's only thank you from now on. Okay, if I could go back to that slide, I would put it up. So the question was, so generally in the Lambda architecture, okay, there we go. We have this picture of Lambda architecture, there we go, where, okay, the question was, you always read this, you always read the raw data, or do you read this aggregated data in our implementation?
Right, in the implementation of the batch.
Yeah, so in the implementation of the batch, there's two things that you would call, those things are not exclusive. So let's imagine you want to calculate the number of total clicks this page ever got. I have to read the previous batch, which has, so in our view, we don't necessarily have to, but we assume that batch 0 was correct when we ran it on Hadoop, and that we don't read all of history. We only read the deltas that came in since batch 0 was atomically committed and totally correct in the system of record. And we take those two and add them together.
Okay. So
we don't read through all history.
Right. So how often is it the case then that you do have a batch that is incorrect? Say the data was bad or corrupted or there's a software bug that was pushed out, and so batch 0 is wrong, and you're now up to batch 6.
Yeah.
And so obviously all of the incremental state updates between 0 and 6 are wrong.
Yeah.
So does that happen very frequently, and how do you kind of deal with that?
Well, of course, naturally, because Twitter is the finest engineering on the planet, we very seldom introduce bugs into our system. But on the rare occasion that bugs have been introduced, and this has happened, yeah, you can go back, and if you set a retention policy such that you're keeping enough of those batches, you can just say, like, let's suppose we get to by batch 2, we realize we screwed up. I mean, there's only so many batches on the screen, but let's imagine. By batch 3, we realize we screwed up in batch 1. So what we do is we go back and we can update the state pointers of all the things that are keeping track of these jobs to say that actually we're only at batch 0 again, wipe out those directories that have been gone since, and the system, the scheduler can just like rush ahead as fast as it can to catch back up. So it can kind of deal with that, but we don't have anything particularly special other than understanding logically how these things connect.
Okay. And is that built into the Summingbird library? Or no?
Yeah, it is. So there's this abstraction of how you keep track of state, and we implement that abstraction in our own internal thing, but I think that abstraction will be relatively easy to port to other schedulers such as Azkaban or et cetera. So,
cool.
Yeah,
Thanks.
I think it's very portable. Next question, over here, yes.
So not all your jokes fell flat. So when you're doing the data
Thanks,
cubing,
Ken. Ken's a plant. Actually, I'll pay you later. Go ahead, Ken.
So when you're doing the data cubing thing, and you're doing the massive aggregation, like all tweets ever for the history of Twitter,
Yeah.
you usually get data skew. Then like one unlucky reducer that winds up dealing with that everything key
Yep.
has skew. How do you deal with that? Do you do like sub-aggregations and a later?
Yeah, it's a good question. So how do we deal with the hotkey problem, or especially if you have this all key, all the tweets ever, or a big concatenation of all the whatever you like. So if the operation, so we've talked about monoids, and monoids always have the property of associativity, and that we leverage, but sometimes they have the property of commutativity, in which case A plus B is the same as B plus A. And for those, Summingbird understands that it can do pre-aggregations on the mappers. And so there's where tuning comes involved, and I would like to get to where it was a little bit more auto-tuning. Both on Storm and on the Hadoop pictures, it can keep a buffer up of many of these things on each of the mappers. And when that buffer gets relatively large, it will then do the same thing on each of the mappers grouping. And these kind of keys, they totally eat it for lunch, because it's like each of the mappers has that one key over and over and over again, and we do that reduction before we send it on. So it works, like that case is pretty okay. The bigger problem is when you have a non-associative monoid, which is not very common, then it really you have pain.
But now you're introducing latency in this.
Yeah,
process.
actually. So now you have a trade-off where if you can afford the bandwidth, you output every time. But if you can't afford the bandwidth, then you have to pay in latency. I mean, there's no free lunch. Somewhere something's got to give. So I agree. Yes. Next question.
When you showed the Scala code for your word count, there were some static classes in there, like status containing fields, presumably. I was wondering, how does Summingbird manage schemas, and in particular schema evolution, for the tuples flowing through the system?
Right, that's a good question. How do you manage schemas and tuples in Summingbird? And so my answer is, like, actually, I'm not really into the whole tuple thing. I think the tuples were like a little bit of a bad idea for the data engineers in the crowd. If you want to write SQL, I think SQL is a great thing for like tuples and schemas. And I think mixing the tuple model too much with like the kind of data engineering distributed collection model has not been such a great experiment. So Summingbird, like Spark and like the typed API in Scalding, there's no tuples. There's either event streams or they're key value streams, like keyed streams, but that's it. And so in this case, those keys could have been anything. They could have been like my fat object that has some hash code that you can group on, but there's no schemas here. So they're just types. And the compiler can see if those types are correct, because again, this is just Scala code, and it's not going to compile if you do something goofy. But that pushes the evolution question off to the user. In our case, we use Thrift. We evolve schemas by generally adding optional fields to our data, but many people use Avro, and they have like a different methodology for how they do schema evolution. But it would always be just the object here, and the compiler sees the full type the whole time. I don't know if that answers it.
Yes, in part, but you say the onus of managing the schema evolution is pushed onto the user.
Somewhat.
But does that mean when you evolve your schema, you need to update all of your downstream consumers first?
I mean, yeah, schema evolution is a massive pain. So if you totally do that, yes, you do. Unless you wind up rendering like the final, like you might update your schema, it might be the input, but the output might be the same. Like we could update the way tweets are stored, but the bottom line question of how words are still strings and their counts are still longs. So, I mean, you know, not every schema change results in an output change of the job. Right. Okay, so I'm out of time now. Please come talk to me about Summingbird later at Posco, Oscar at Twitter. Thanks a lot. Bye-bye.